Good morning, everybody, and we are today going to do one or two problems for the chapter 8, and I wanted to go over some of the concepts in these office hours. So basically what we were looking in chapter 8 is angular quantities. So you're talking about angular motion. Uniform circular motion was discussed in chapter 5 when we were talking about objects going in circular fashion. But rotational motion can also be applied to solid spherical objects. And we can talk about angular displacement here. We can talk about angular velocity here. So if you remember what we discussed in chapter 8, part 1, angular displacement is basically the display, how much the angle is getting displaced. So if this represents theta 0, and then it moves a little bit, and then over here I have another angle. So the change from initial angle to the final angle becomes your displacement in angular displacement, right? And similarly, we can look into angular velocity. Angular velocity is nothing but in angular displacement over change in time. And if you remember, we discussed theta has a relationship with arch length and the radius of the rotating sphere or circle. So you can replace theta by L by R, and then you can have a relationship between omega and linear velocity. So in the same way, we have angular acceleration, which is denoted by alpha. Okay, so alpha is a Greek letter, omega is also a Greek letter, and the units for omega are radians per second. So angular acceleration, which is angular alpha, angular acceleration is final angular velocity minus initial angular velocity over change in time. We can also call this as average angular velocity. And this is represented as delta omega over delta t. And the SI units for alpha, the angular velocity, angular acceleration, is radians per second square. So you see there's a departure from the linear linear acceleration, linear velocity. So they are different. Our linear velocity is v, that is displacement over time, and our acceleration a, that is also called tangential or a simple acceleration, is change in velocity over time and change in time. So there is a you have to understand there is a relationship between angular and linear components of the velocity and acceleration. So understanding this, there is a relationship between linear and angular quantities. You'll say how? All right, so if I have this circle, okay, and this represents the length of the arc. If I started from this position, this represents radius, this represents my delta theta, this represents my, you can say it's theta. So there's a relationship between theta, L, and R. Theta and R represent radial quantity, while its length of the arc is a linear stretch. You're going linearly. So that's the first linear relation, and linear and angular quantities are related. Theta is somewhat displacement. Delta theta is displacement. Delta x is also displacement. Delta L will also be displacement. So there is a relationship. In the same way, we have angular velocity, which is nothing but delta theta over delta t. So instead of writing theta, if I plug in this formula over here, this becomes del by delta t L over R. So I'm substituting for theta. Now this becomes 1 over R comes out because radius doesn't change, so it's not part of the um, change. So radius throughout will remain same. So we have delta L over delta T. Now delta L is a replica of delta X or delta Y. So it's a displacement. So we can simply write omega, that is the angular velocity, as 1 over r multiplied by v, which is the tangential velocity. So the velocity v, it's the linear velocity, while as angular velocity is towards the circle. It's central to it. It's the angular velocity, it curves in, while as the tangential velocity, which is a linear velocity, is always tangential to the circle or tangential to the arch. So therefore, there's a relationship between linear velocity and angular velocity through radius r. I explained this in my video lecture, that angular velocity is fastest towards the center because there's a reciprocal relationship between radius and angular velocity. So linear velocity can also be represented as, if I multiply both sides by r, it becomes omega r. So you have to remember how we are representing relationship between linear and radial quantities. We can do the same for acceleration. Acceleration is delta omega over delta t. All right, but omega is v by r. If I substitute this formula into this formula over here, so instead of writing omega, I can write v by r directly from here, and then 1 by r can be taken out. So this becomes delta v over delta t. What is delta v by delta t? Delta v over delta t is tangential acceleration. It's the acceleration that an object or a particle or a body experiences tangential to the circle, while as angular acceleration is radial, it's inwards. So this becomes alpha, sorry, not alpha, this becomes a over r. So there's a relationship between alpha, a, r. Let me write it here. Alpha is equivalent to a over r. This is the tangential acceleration, radial acceleration. They have a relationship. So we'll be looking into some of the formulas over here. Also, I should say that we have a centripetal acceleration AC, one more form of which you saw in circular motion, that is v square over r. But what is v? We will substitute this v from here over here, and the centripetal acceleration becomes then, if you substitute this v as omega r into v square over here, you will get omega square r. If you work on this, there is another form of acceleration which is related to the radial components, and you'll get it as omega square r. So we'll use these formulas in some of the problems. Now let us look at one of the examples. So there is calculating the angular acceleration and deceleration of a bike wheel. Suppose a teenager puts her bicycle on its back and starts the rear wheel spinning from rest to final angular velocity of 250 revs per minute. Okay, so understand, it's just like saying kilometers per hour, but for velocities we'll use revolutions per minute or radians per second. That's what we have to convert. Our objective is convert revs per minute into radians per second, because that is the SI unit of angular velocity. Okay, so you have to find the angular acceleration in radians per second squared, And then the part B says, if she now slams on the brakes, causing an angular acceleration of minus 87.3 radians per second square, that means the acceleration is reducing because she's slamming the brakes. So how long does it take the wheel to rotate? I think whole of this pasted here. So we'll go ahead and solve this problem. So basically what is given? Let's write down what is given to us. We have been given delta omega, where delta omega is omega minus omega naught. So a teenager puts her bicycle on its back and starts the rear wheel spinning from rest to final angular velocity. Omega naught is 0. Your omega is 250 revs per minute. If you have been watching my video, if you watched the video number 1, you can convert your 250 revs per minute into radians per second. Okay, that is how you do it. 250 revs per minute doesn't allow me to erase. Revs per minute, multiply this by, what is 1 rev? 2 pi radians over 1 rev, and multiply this also by 1 minute is 1 minute over 60 seconds. Okay, so let's do this neatly here. Omega is 250. Rev and rev will go away. So I have multiplied by 2 pi radians because the radian rev part of it went away. Instead of minute, I have 60 seconds. If you multiply all of this, you should get 26.2 radians per second is the final angular velocity for part A. Okay. And is there any conversion needed? No, I think everything else is in place. So we'll work on the math problem in the next part. So part A asks you to find out the angular acceleration. So you have to find out the angular acceleration. And we know angular acceleration is given by change in angular velocity over time. So you already know the change is 26.2 divided by the time that is given as 5 seconds. 26.2 radians per second divided by 5.00, all of them are in 3 sig figs, 5.00 seconds. If you work this, you will get the angular acceleration as 5.24 radians per second square. This is your alpha and not the tangential acceleration, which is meters per second square. That is not it. So this part 2 asks you to find out if she slams the brakes. So what if she slams the brakes, causing an angular acceleration of, so that means now the velocity is changing and the final velocity is 0. That creates an angular acceleration of 87.3 radians per second square. So she must have slammed the brakes really fast so that the change is really abrupt, and we get an angular acceleration of minus 87 because it's reducing the speed. You have to find how much time it takes her to stop the wheel. The wheel is not in rotation. You can understand the scenario also from the exercise bikes that we have. You can get there and think about what happens to the wheel. So here the angular velocity has now decreased from 26.2. So that means our initial angular velocity is 26.2 radians per second. So whatever was the final in the part 1 is the initial for part 2, and omega becomes 0. So therefore my change in angular acceleration or angular velocity is minus 26.2 radians per second. So now we know that alpha is equivalent to delta omega over t or delta t. You know this, you can find this quantity. So delta t or t, whatever you want to put, you're fine to put it as t, is equivalent to delta omega over alpha, which is already given to you. So now that we know that this is minus 26.2 radians per second, and alpha is already given as minus 87.3 radians per second square. So when you work on these units, you will get the value as second. And in the end, you get an answer of delta t equivalent to 0.300 seconds. She must have really slammed the brakes hard to stop it in such a short interval of time. So that is how you do these problems. So this is one example, and I thought that in addition to other problems from your problem worksheet, which is uploaded on the Blackboard in the online class section of this week, we can always look at some extra problems. So we also have one more problem. I thought this was interesting to bring it to the office hours. Calculating the angular acceleration of a motorcycle wheel. So a powerful motorcycle can accelerate from 0 meters per second to 300 meters per second in 4.20 seconds. What is the angular acceleration of 0.320 meter radius wheel? Now you must start thinking, what is given here? What is it giving us? The units are meters per second. So surely this is not radial, or this is not angular velocity that is given. We have been given V naught as 0 meters per second, and we have been given V as 30 meters per second. So, and time is given as 4.20 seconds, and also radius of the wheel is given. So he's asking us to find out the radial acceleration. We are not looking for tangential acceleration. We are not looking for tangential velocity. We are going to look for radial components. And if you remember, I reviewed some of the formulas that relate radial to the linear components. So R is given as 0.320 meters. And we know that your alpha, that is the acceleration, angular acceleration, is basically given by tangential acceleration A over R. So can I find the tangential acceleration? Yes, I can, because I have been given the three quantities. So I can proceed that way. And you can pause this video if you are watching the recording, and if you are already in session, so even then I can stop for a little while and you can proceed with solving the problem. So basically we have been given this value, and then you can also find out the alpha. So in the next slide we'll start working on this. So this is a simple problem where we are relating the tangential component and the radial components. Basically, my tangential acceleration, which we simply call A in our normal scenario, but since we are doing rotational motion, it is important to know the distinction between AT, AR, and alpha. So you know that AR is the centripetal acceleration, which we did in previous chapters. And we just now found out it has a relation with radial component as well as, so it's omega square R, where we can relate it to the angular velocity. This is the radial velocity. And alpha is basically given AT over R. And your tangential component is simply what you were used to solving for acceleration as change in velocity over time. So let us first find the change in velocity. That is 30.0 minus 0 over the time. That is given as 4.20. So then you solve this and you will get answer as 7.14 meters per second square. So you found out 80. This problem is not asking us to find out the centripetal acceleration. You can go ahead and find it on your own because you'll the omega, but that's fine. You'll have to find the average acceleration. So we can't do it yet. We can do it once we know kinematic equations of rotational motion. So go ahead and find the second part of it. We have 7.14 meters per second squared divided by the radius, which is 0.320 meters. And once you work on it, you should get the value as 22.3 radians per second square. A good question at this point will be, how do you know that you can put this unit as radians per second square? Well, if you have to remember, units of radians are dimensionless and appear in any relationship between angular and linear quantities. So I want you to note this. Do not get confused. If you are converting from meters per second square and this is the SI unit, this is the SI unit, and you are looking into a radial acceleration, you can easily write radians per second square in it, because units of radians, this is something that confuses the students. Units of radians are dimensionless. And appear in any relationship between angular quantities, angular and linear quantities. And linear quantities. So you should not stress too much about the unit. If you see, it's very difficult to write here. Okay, so if you see there's a meter per second square for tangential acceleration and there's a meter for a radius, you can easily put the unit of angular acceleration as radians per second square. So in the next part of chapter 8, part 2, today we are going to I'm going to post second part of the chapter, which is the last part basically, but we'll continue working on more problems and there will be a review next week, and also the multiple choice. And I will also post what is going to be on the exam. Is it cumulative or is it going to be some specific chapters for the finals? So watch out for the information for final exam. Part 2 will come by tonight. You should see the part 2 of chapter 8, and that will be the end. That is rotational kinematics. So you saw kinematic equations in linear motion in chapters 3 and 2, and we similarly have rotational kinematic equations for rotational motion as well. This is the easiest chapter so far, and should not be too much stressful for you to practice problems in this one. Keep on coming to office hours if you have any questions. All right. So I'll end the recording here and